Okay, thank you very much for the invitation. It's a pleasure to be here. This is my first time in Lisbon. So yeah, I'm going to talk about in the first part of my talk about some things that I did during my PhD, and then in the second part I will talking about some ideas I've been thinking about more recently. So so here is the outline of the talk. I will first give some general introduction about the sort of theories that I'll be considering, and a general discussion of the Cauchy problem in these theories. Then I will talk about some well-positiveness results in theories with second-order equation, then discuss the situation with higher derivative equations. So okay. Then we start with motivating this work. So obviously, this is sort of motivated by gravitational wave astronomy and the recent progress in this area, that now we are able to perform, we'll be able to perform precision tests of general relativity, a strong field, highly dynamical regime. But currently, the detection procedure involves searching for signals that match with certain theoretical templates. And these templates are produced by numerical relativity simulations of mergers of compact objects. And these numerical simulations are first of all, they're highly expensive, and secondly, they rely on solving Einstein's equations. So if we want to find some new physics beyond GR, we have to do the same kind of simulations, different theories. Now, there are at least two types of problems with this. The first one is that there are a lot of modified theories of gravity being proposed in the literature. So it's far from clear what theories should be focused on. And secondly, as I said, doing numerical simulations is not so straightforward. Beyond the details of numerical problems, there are also mathematical restrictions. And most notably, the theory that we want to simulate must have a well-posed initial value formulation in order to be able to solve the equations numerically. So there is a possible answer to the first problem that I raised, which is which fields, and that is provided by the effective field theory framework. So this provides a framework to parameterize strong field deviations from GR, and this simply amounts to enumerating all the possible higher derivative terms with the desired field content and symmetry in a low energy effective action. And these higher derivative terms generically arise from some severely complete theory by integrating out certain massive degrees of freedom. Maybe I should say at this point for clarity that in this talk I'll be considering theories that intend to modify GR in a high energy regime rather than in long distance regime, because there are some theories that intend to address the explain dark energy or dark matter by modifying GR. But in those situations, when you want to alter the long distance physics, this sort of derivative expansion is not really suitable to build theories like that. So in this talk, I want to think about high energy sort of modifications of GR. So to give you an example of how these effective field theories are built, let's consider the example of vacuum gravity dimension. So here are desired symmetries, diffeomorphism invariance, and our dynamical fields that are only dynamical field in vacuum. It's just a metric tensor, and you can systematically build this low energy effective action. So the first term in this expansion is just the standard field Einstein-Hilbert term, which contains two derivatives of the metric tensor, and the leading corrections to this contain four derivatives of the metric tensor and their quadratic in curvature, and so on. One can similarly enumerate all the possible higher derivative terms involving the curvature. And as you can see, these higher derivative corrections are expected to be suppressed by some length scale L, which is a UV length scale. And the idea is that to study processes at energies which are small compared to this just the inverse of this length scale, then one can just truncate the series at some finite order. And this, as I said, this makes sense if the curvature is small compared to the scale set by this UV length scale. And this is what we'll call the weakly coupled function. But to make it clear, one can still study strong field phenomena in the astrophysical sense of the word. So, for example, one can study the nonlinear dynamics of black holes, which are sufficiently large compared to this UV length scale, using weakly coupled EFTs. Okay, so let me just highlight at this point some issues about this approach. So, so this truncated EFT generically has equations of motion that is higher than second order derivatives. And the reason why this is an issue is that, well, first of all, for such theories, the initial data set contains higher derivatives. And this means more degrees of freedom. But what's often found is with these types of higher derivative equations that the solutions associated with these extra degrees of freedom may be pathological in the sense that there's exponential growth on a microscopic time scale. So very quickly the solution runs away to a regime where the EFT is no longer expected to be valid. This is referred to as Ostrogradski boost. So this is the sort of expected generic behavior, although there's some specific counterexamples where higher derivative theories seem to work okay, at least in some situations. The second issue is that, as I will discuss later, the well-posedness of the initial value problem requires that the highest derivative terms in the equations have a special structure, which I will explain later. But from an EFT point of view, it is actually that these highest derivative terms in the equations should be sublinear. But as I said, well-posedness is primarily determined by these highest derivative terms. And this special structure of the highest derivative terms required for well-posedness is not guaranteed in general. So these are the main issues. However, as I will now explain, in some theories, one can use perturbative field redefinitions to shift some of these problematic operators in the effective action to higher order, so that the theories that include the leading order EFT corrections at least as second order equations. So coming back to this example of that EFT, one can actually use these perturbative field redefinitions to shift the terms that involve the Ricci tensor to higher orders. And then what we are left with, the dimensions, is that there's only one leading order correction to the Einstein-Hilbert term, and this is the Gauss-Bonnet. This can be chosen to be the Gauss-Bonnet term. So this term is only non-trivial corrections to Einstein's gravity, higher dimensions. But if suppose we are in higher than 4 dimensions and we truncate this theory at the further levels here, then And the resulting theory, Einstein-Gauss-Bonnet gravity, has second-order equations, so we don't have to worry about these ghosts that I mentioned in the previous slide. However, if you are in just 4 dimensions, then, as I said, this theory is just this term, the Gauss-Bonnet term, is a total derivative, so it doesn't give any non-trivial contributions to Einstein's equations. And then the leading order corrections to Einstein's gravity start at 6 derivatives. And if you truncate at 6 derivatives, effective action, and the resulting equation of motion is higher than second order, and we have to face the problems that I mentioned in the previous slide.
Sorry,
yeah.
Can this procedure of perturbative redefinitions be done also in higher orders, right? Because it's a leading order correction only.
Yeah, sure. You can basically, with these perturbative field redefinitions, basically like shift terms that are proportional to the Ricci tensor and derivatives of the Ricci tensor to higher orders. So that's basically the idea. But yeah, I primarily want to focus on the leading order corrections to Einstein gravity for the moment. Okay, so this is the case of vacuum gravity. But if we include matter fields, we might be in a slightly better position. So consider an additional real scalar field, 4 dimensions, and assume additional parity symmetry. Then one can play the same. And so at leading order, at the 2 derivative level, we have the Ricci scalar, just the standard kinetic term for the scalar field, also have a potential, and then the leading corrections to this minimally coupled Einstein scalar field theory. So after field redefinitions, we can get to the 4 derivative corrections, which only includes now sort of a scalar field self-interaction, a coupling between the scalar field and the Gauss-Bonnet variant. And so now, even in 4 dimensions, if we truncate this effective field at the 4 derivative level, then we end up with a theory which has second-order equations. And this resulting theory has also kind of interesting phenomenon. For example, black holes have scalar hair. So this effective theory truncated at the 4 derivative level, this Einstein scalar Gauss-Bonnet theories, is the theory that I will focus on the first part of my talk, although basically anything I say is equally valid for any other theory which has second-order equations. Okay, so now let me turn to a brief discussion on the Cauchy. So what I mean is that we want to consider a dynamical formulation of this theory. So we want to set up some initial data on a Cauchy surface and use the equations of motion of the theory to evolve this data in time. So we say that the initial volume problem, as set up here, is well used if there exists a unique solution to the equations of the theory, and secondly, the solution depends continuously on the initial data suitable norm, which means that take solution at time t, and compute some suitable norm, some typically a Sobolev norm, and we say that it depends continuously on the initial data if it satisfies an inequality like this. So solution, normal solution at time t is bounded by some continuous function times the norm of the initial data. So this essentially means that if you change your initial data slightly, then the solution at later times won't be very different, also quite important if you want to run numerical simulations, because this inequality essentially guarantees that your simulation is robust to numerical errors. And then sometimes there's a third criterion, which is that the solution exhibits causal propagation, but I won't really be discussing this third point very much. So this is the requirement for well-positiveness. Now, let me give a very brief example on how things can go wrong. So let me give you an simple example, equation that is still an initial volume problem that is still fixed. So consider the 2D Laplace equation. In here, they don't want coordinates by t. Give an initial value for the field and its first time derivative. And in particular, consider the following one-parameter family of data that's written down here. So for the field, this is the initial data. For the initial time derivative, we just set it to 0. As you can see, as n approaches infinity, Fn and Gn converge to 0 uniformly. So you would expect that the solution to this initial value problem could also approach 0 and goes to infinity. However, this is not quite the case, because one can actually write down a specific, an exact solution to this initial value problem, which is given here. But now take the limit for any positive but finite value of the time, and then you can see that the solution actually approaches infinity. So it's very much not to be expected from the expectation of data that is approaching trivial data, produce the solution that approaches infinity. So this means that the solution does not depend continuously on the data, and this initial value problem is not well posed. So this is just to illustrate how things can go wrong and what it actually means that solution doesn't depend continuously on the initial data. But okay, so how do we actually investigate well-positiveness? Well, there's a very useful result in PD theory, which relates simple algebraic condition, the hyperbolicity of a system of PDs to well-positiveness. So I will explain the concept of hyperbolicity in the next couple of slides. So consider a first-order linear system of PDs. For the moment, let's assume that the coefficients of this PD are constants. So since these coefficients are constant, we can just take the Fourier transform and write down formal solution to this PD in terms of the Fourier integral. And you can very easily work out that the solution will look like this. So it's an integral here. But in order for this solution to actually exist, this integral needs to exist. And for this integral to converge and the initial volume problem to be balanced, we need this matrix that appears here. We need this to be bounded by some function of it. So it has to be bounded, in particular, independently of this wave number psi. So it's easy to see that if this type of bound is satisfied, then this integral will make sense. So then, with a bit more work, one can show that this type of bound actually implies that this matrix MK interacted with a wave number psi. So this condition is equivalent to this matrix admitting so-called symmetry. So, but K of psi, which just means a positive definite and bounded Hermitian matrix matrix that satisfy this condition. So essentially symmetrizes this matrix M that we essentially constructed from the highest derivative terms. So we say that P that satisfies this condition is strongly hyperbolic. And as I said, the initial volume problem for strongly hyperbolic P is local values. At least we've shown this now in this simple example of constant coefficient first order PDs. Now, more can be said about similar things can be said about more difficult equations. So if you consider first order but nonlinear PDs of this form, and you construct this matrix M by taking derivative of f with respect to the first order spatial things. So again, this matrix M is essentially telling you coefficients of the highest derivative term, PD. But now it depends on, since this is nonlinear, it can depend on coordinates and field itself. And we, in this situation, we define strong hyperbolicity. Similarly, we say that a PD is strongly hyperbolic if this matrix M admits a positive definite symmetrizer, which again now depends on all these things. And so compared to the situation of constant coefficient PDs, we add the additional requirement that the symmetrizer must depend smoothly on all of its arguments. So all of these arguments. So it has to be smoothly dependent. These arguments has to be bounded. It has to be a symmetrizer. It has to satisfy this. And it can be shown with quite a bit more work that the initial volume problem for strongly hyperbolic nonlinear PDs is also locally balanced. So here so far we only considered first order systems of PDs, but similar things can be done with higher derivative PDs. So one can just introduce auxiliary variables to reduce higher derivative system to first order systems, and then play this to try to construct these symmetrizers. Just a couple of quick remarks about this. So as I said, so the necessary condition for M to admit a symmetrizer, so the system is strongly hyperbolic, is that this matrix M has to be diagonalized for real eigenvalues. And if additionally the eigenvectors of M depend smoothly on the psi, this is wave number for any psi, then one can use the eigenvectors to construct a symmetrizer. And also the eigenvalues of M are called characteristic speeds. They basically describe the speeds of propagation as described by the equations. So the takeaway message from this couple of slides is that the PDE system has a locally balanced initial volume problem if it is strongly hyperbolic. And strong hyperbolicity is, as I said, it's just an algebraic condition that refers to the highest derivative terms in the PDE. So this is the main tool to investigate well-posedness for the theories that I'm considering. Okay, now just very quickly. So there could be issues even with strongly hyperbolic conditions when they are nonlinear. Very simple example is given here. So consider this initial volume problem. One can write down an explicit solution given here. And as you can see, the solution blows up as t goes to 1. So this is the reason for emphasizing the word local values is exactly this. because generally nonlinear PDEs, it's a generic feature of nonlinear hyperbolic PDEs that solutions, the generic initial data, can blow up in finite time. So hyperbolicity actually just guarantees validness for at least some small amount of time, but it can, solutions can blow up and validness can break down beyond a little bit of, after a little bit of time. So, but of course, for special PDEs and special initial data, one might be able to do better. Famously, there is a proof of nonlinear stability of mean-constant space-time in GR. So that's an example of global validness when validness holds beyond a small amount of time. But also there are a lot of black hole stability results in GR, but they require a lot more work than just investigating the hyperbolicity of the system. Okay, so so in the case of gravitational theories, there is an additional problem that needs to be addressed. So clearly, gravitational theories are the equations of motion in gravitational theories is diffeomorphism covariance. So in a strict sense, if you write down Einstein's equations, the solutions themselves are never unique. You know, all these consider some diffeomorphism that produces some new solution. To get to a well-proof initial value formulation of diffeomorphic invariant theories requires finding a good gauge, a good way of fixing the gauge. And in GR, the simplest way to do it is to deploy the harmonic gauge, which is essentially requiring that coordinates satisfy a wave equation. And so if we denote by HV this quantity, which is basically a box operator, coordinates, or also written in terms of Christoffel symbols, so this quantity vanishes, that's the harmonic gauge. And one can carry out the gauge fixing by adding a suitable combination of the derivatives of the gauge to the equations. So the idea is to modify the highest derivative, the structure of the highest derivative terms in Einstein's equation. So if you actually consider the trace reversed version of the system equations, then the effect of the gauge fixing is more familiar. So you can see that the effect of the gauge fixing is just to reduce Einstein's equation to a nonlinear wave equation for the components G. So this is now just Cox operator acting G plus some lower terms. So then this equation is clearly strongly hyperbolic. It can be shown that the initial value problem for the harmonic gauge Einstein's equation is locally well posed then. So this is the famous result by Cauchy in the 1950s. She's actually celebrating her 100th birthday today. So there's a conference I heard happening now. So okay, so in GR the harmonic gauge works very nicely. So now let's get back to this scalar tensor mechanisms. Once again, this is action theory. The equations look extremely ugly, but they are second order derivatives. So we have the gravitational equations, it's Einstein's tensor plus a bunch of ugly terms, and scalar equation similar. We have Cox phi plus a bunch of curvature and scalar derivative terms. So what do we do with this? So the first problem, there are a lot of problems with these types of equations. The first issue is that the equations of motion may become elliptic when the higher order corrections to Einstein's equations are large. So perhaps by higher order corrections, I mean these terms that come with alpha and beta. So the terms that come from these terms of the equations, but they actually produce contributions that are second order derivatives of the equations of motion, but they're highly nonlinear and complicated. So what I'm saying is that if the terms multiplied by alpha and beta become too large, then the character of the equations may become elliptic. And I showed you that things go horribly wrong when the evolution equations of the theory become elliptic. So this behavior is actually analogous to the so-called trichome equation, which is written here. So you can see that it is hyperbolic. It has the character of the wave equation when t is negative, but becomes elliptic when t is positive. So in these theories, the equations may dynamically change character. So that's one issue. But we can sort of, if we restrict to the beta population and assume that these high order EFT corrections and the equations are small compared to Einstein scalar terms, that is, its alpha and beta terms are sufficiently small, then we might be able to prove values. Yes, in that case, the equations might be hyperbolic. But well-posedness is not very obvious if you restrict to weak couplings, because as the following example demonstrates, hyperbolicity is a rather fragile property of the system. So consider two scalar wave equations depending on a parameter epsilon. So when epsilon is 0, then clearly it's just two decoupled wave equations. And if you set up initial data for phi 1 and phi 2, then the Cauchy problem is well posed. But you can check that if you consider any non-zero value of epsilon, however small it is, then the system becomes elliptic. So you can actually spoil hyperbolicity by adding very, very small terms to a system.
This in 1 + 1 dimensions
Yeah,
again.
yeah, sure. 1 + 1 dimensions, yeah. Okay. Yeah, and some previous results. So as I said, the Einstein's equations admit well-posed initial volume formulation with harmonic gauge. So the obvious thing to try is to try and apply the harmonic gauge in these scalar tensor theories. But as it turns out, the harmonic gauge is not enough. It doesn't produce a strongly hyperbolic system when applied to these Hornetsky type theories or scalar tensor theories. And there are some attempts to do numerical simulations without well-posed formulation. So, for example, if one restricts to spherical symmetry, then one can still run simulations. And also there have been attempts to produce numerical simulations perturbative couplings, which on some level makes sense because if you regard these theories as EFTs, they are sort of constructed in a perturbative way at the level of the action. But the problem is that in a dynamical situation, there are secular effects. So perturbation theory might break down very quickly, even in situations where the EFT equations of motion are still valid. So you could, for example, consider a binary where these EFT corrections are locally small, and you could in a perturbation theory, perturbative method in the coupling, you might get the phase is completely wrong. So you so bottom line is that you could have situations where effective field theory equations of motion are still valid in the sense that these EFT terms are small compared to the GR terms, but the solution itself is very far away from a GR solution when small, locally small effects accumulate over a long time. So perturbations, yeah.
Clarify the first statement.
Yeah.
So our density is not strongly hyperbolic, but is it also not well posed? Or what is the relation between the two in that case?
So the first statement is that in harmonic gauge only, the equations of motion for density theories is not strongly hyperbolic, and therefore
does that imply it's not well posed
in harmonic gauge?
In harmonic gauge, yeah.
Yeah. Any other questions? Okay, so let me now move on about posedness results for theories with second order equations. So as I said, the original harmonic gauge doesn't work for these theories, but it turns out that a slightly trickier choice of gauge does work. So in order to describe this gauge fixing, we have to introduce two Lorentzian metrics, which are denoted by G tilde and G hat. And we will require that these auxiliary metrics satisfy the following conditions. So we require that the causal points, tangent space, form a nested set so that they do not intersect the center. And in particular, we want to require that in the tangent space, the causal point of the physical metric is the innermost one. And it also implies that in the tangent space, if you look at the inverses of these metrics and the ordering of these causal points just turns around. And we are going to use these two auxiliary metrics to set up a tricky choice of gauge and a tricky way to fix the gauge. So we introduce a modified harmonic gauge condition using one of these auxiliary metrics, G tilde. And this gauge condition is similar to the harmonic gauge, except it involves this other metric, G tilde. So it's basically the box operator acting on the coordinates. That's our modified harmonic gauge condition.
But the Christoffel symbols are from the physical metrics.
The Christoffel symbols are from the physical metrics.
Sorry.
Yeah. And the gauge fixing is carried out similarly as in the case of GR, that we add a combination of the first derivatives of this H quantity to modify the gravitational equations, except this tensor B hat now involves the other auxiliary metric B hat. And so in this situation, the effect of the gauge fixing for now is not not as nice as in GR, that it eliminates some terms and very obviously reduces the system to a set of nonlinear wave equations, but we will see why this particular gauge fixing works in a moment. But of course, so this is the modified harmonic gauge equations of motion that we are proposing. And so, of course, setting G tilde equals G hat equals G just recovers the usual harmonic gauge equations of motion. So the statement about this gauge fixing, about these EFTs, is that using these modified harmonic gauge equations of motion, then this system of equations admits a local values initial one formula. initial volume problem in Einstein's scalar theory. And then if you include the weak coupling, four derivative corrections, then we have the same conclusion, provided that, again, that the null points of these metrics are related as shown in these figures. And as I said, similar results apply to essentially any theory which has second-order equations. So any Lovelock or Ness theory, provided that we consider weak couplings. So this is the statement. Now let me explain why the main idea why this works. So as I said, to show that the initial volume problem associated with these equations as well, we want to essentially show that the gauge fixed system is strongly hyperbolic. And as I said, strong hyperbolicity requires diagonalizability of a certain matrix M of Xi, which is constructed from the coefficients of the P and depends on the generic vector Psi. And of course, it sort of depends on the field configuration. So you can think of it as linearizing the nonlinear system around a generic background and showing that the linearized equations are hyperbolic in every possible background. And so, as I said, briefly mentioned that the eigenvectors of this matrix M are related to polarizations of high-frequency solutions of these gauge-fixed equations, and the eigenvalues represent populations of these modes. And so, in these theories, in GR and scalar tensor theory as well, we can distinguish three types of these mode solutions. First ones are pure gauge modes that sort of describe high frequency infinitesimal diffeomorphisms that by construction will propagate along the null of G. The second mode solution is yeah.
Any that gauge mode always propagate faster than the speed of light.
Yeah, so that's basically our assumption on the causal cons of these auxiliary matrix guarantees that the speeds of propagations of these non-physical modes remain subluminal, so less than speed of light. But even if they are higher than speed of light, it's not really an issue because these are unphysical modes. So it's not really describing any type of physical process, but you can sort of, in a numerical solution, you can sort of see them because you always have like some small constraint violations, but it's convenient to have to make the speeds of propagations of these modes to be less than speed of light. So hence the condition. So this condition that for example here the innermost form is that of the physical metric guarantees this, but actually you could make this same statement if it wasn't the innermost form. The point really is that they sort of form a nested set. Then it does the job, but yeah, the way it's drawn in this picture guarantees that the non-physical modes, the unphysical modes have speed less than speed of light. So as I was saying, the second group of these mode solutions is called gauge condition violating modes. And again, by construction, these will propagate along the null G hat. So these are modes that violate a high frequency version of the gauge conditions. And then the third group, so these first two groups are sort of unphysical mode solutions. And the third group are physical polarizations. So in the case of Einstein's scalar, just a minimally coupled theory, they will of course propagate on null or G. So this is really just saying that scalar and gravitational waves in that theory propagate with the speed of light. But once you include these EFT corrections to GR, they will no longer propagate with the speed of light. They will propagate along some complicated characteristic hypersurfaces that are in some sense almost null as long as the theory is weakly coupled. So a cartoon of this is shown in these figures. We have two derivative scalar tensor, the Einstein scalar for theory. Then the cones will have this nested structure. And then once you include these EFT corrections, the characteristic hypersurfaces will have some more complicated geometry, but as long as they're weakly coupled, the surface will be always contained within the causal poles of these two other methods. And so the important point here is that this hypersurface is gauge invariant. So so as long as you choose the auxiliary matrix in a way that this hypersurface is contained also points of this matrix, then you can guarantee that the system of gauge fixed equations are strongly hyperbolic. However, in situations where this characteristic hypersurface is not a hyperbolic, that doesn't have a hyperbolic character, then the theory breaks down independently of the gauge choice. Yeah.
3 minutes.
Okay. Okay, I'll wrap it up. Okay, so I just wanted to say that the reason why this construction works and the original harmony doesn't is because, as I said, so when you look at the harmonic gauge case, then all these 3 types will propagate with the same speed. So they will propagate along the null of the physical metric. But once, so this matrix M that needs to be diagonalizable will have a very high degree of degeneracy, which is fine in GR because it's a special theory. But in these, once you include these EFT corrections, then this high degree of degeneracy is now problematic. And this matrix M will no longer be diagonalizable in the case of those theories. But if you introduce these extra metrics and separate the speeds of propagations of different types of modes, then you can sort of undo this high degree of degeneracy, and that is why this modified harmonic gauge condition works. Okay, so very quickly, I only mentioned the condition on these G tilde and G hat metrics. I haven't really given a choice, or given a prescription on how to choose them. A very simplest way to choose these metrics is to consider the unit normal to constant time slices and deform the physical metrics using any where A and B sound suitable functions. They could even be chosen to be constants. And then you can check that A and B satisfy some very simple conditions, then these metrics satisfy the nesting property. And so people have used this type of gauge fixing to perform numerical simulations of black hole binaries, Einstein's scalar Gauss-Bonnet theories, most notably East and Ripley, and later by Forman, East and Ripley. And more recently, a group at Queen University, they slightly modified, they combined the idea of this modified permanent gauge fixing with a common CCZ for formulation used in numerical relativity to provide a slightly different type of Plateau's formulation of Einstein's scalar Gauss-Bonnet gravity, and they also perform simulations of molecular binaries in these theories. So I guess I'm running out of time, so I won't really have time to talk very much about higher derivative theories. So I will skip through these slides, and you can ask me if you're interested in those theories. But the bottom line is that, as I mentioned in the very beginning, there are very delicate issues with higher derivative EFTs due to the presence of ghosts. And people have proposed some regularization procedures which are sort of commonplace in relativistic fluid dynamics. It's called the Muller-Israel-Stewart type regularization of the equations. And so the idea is to try to regularize, try to modify the equations of these higher derivative theories in a way that hopefully doesn't alter the physics in the relevant regime where the effective theory is supposed to be valid, but modifies the equations in a way to make the system hyperbolic, so to cure the maths without significantly modifying the physics. But this is not, this type of idea is not fully understood in a gravitational setting yet, so that is subject to current and future work. So so I'll stop here and let me know if you have questions. Thanks very much.
Well, thank you very much, Aron. We have a few minutes for questions because we started a bit late. So
thanks for the nice talk. A question about the last slides where you're talking about the well-posedness in higher derivative theories using for numerical simulations.
Okay.
That people like.
Yeah.
Figueras and
yeah.
So essentially this one.
I will read the last one.
But the question is, has it been shown for those theories that it's well-posed or only locally well-posed?
Well, local well-posedness has been shown. So that's what I was talking about. Beyond local well-posedness, I mean, it's tough. So even in GR, I mentioned that there are proofs of non-linear stability of Minkowski. The original one is a 500-page long proof by Christodoulou and Kleinerman. More recently, there are more concise proofs which are only 100 pages long. So I mean, this result I talked about is basically the 1950 equivalent of the Choquet-Bruhat result for GR, and it with this paper came out a few years ago. So I guess nobody is really trying to prove like these global nonlinear stability of Minkowski and black holes and in these theories yet. So
results for F1.
Okay.
So there are some results.
I see.
But if you do a simulation in an effective field theory, nothing guarantees that you will forever stay within the regime.
Yeah, of course. This is very much an issue that that there is a dynamical breakdown, and there, but I mean the thing is that so we've shown that there's local well-posedness as long as the theory is weakly coupled. In some situations, you could even have strongly hyperbolic equations when the coupling is not very small, but sort of takes intermediate values. And so, but I would say that so you can sometimes do simulations even in situations which are sort of outside of the EFT regime. But yeah, it's true that when you're forming black holes which are sufficiently small, then you could have a breakdown. So it would be useful to have some diagnostic tools in numerical relativity to try to monitor when the hyperbolicity breaks down. But currently they're not really. There are some proposals, but yeah, it's tricky. Yeah.
So in general, basic general relativity. So what was it that anything to say about whether these modified version for effective also has symmetric hyperbolic?
I don't think that they're symmetric hyperbolic. They are just strongly hyperbolic. I'm not sure if it's possible to come up with a formulation that is symmetric hyperbolic. But I mean, strong hyperbolicity is enough for local well-posedness. So I know it would be nicer to have symmetric hyperbolicity, so you can make sort of you can write the energy functional as a sort of local expression, but I think in these theories it's not possible.
Maybe a comment there, that is bad news for numerical relativists, because we don't really solve the initial value problem, right? We mostly solve the initial boundary value problem.
Yeah.
And treating the boundaries, if the system is only strongly hyperbolic, is a complete nightmare.
Yeah, it absolutely is. So the characteristic, the structure of the characteristic speeds, it's very, very complicated expression. It's very hard to compute. So yeah, it's a big issue for numerical relativity. Yeah.
Right. So thanks. I think your talk was excellent, very clarifying. Like it's a lot. So, but you were very careful when you said the equations of motion are well posed. But do you mean the usual? I'm thinking about the Schucker-Bois theorem. So talking about the evolution and constraint equations, does that include everything?
Yeah, so I was talking about evolution equations. Actually, I also have some results regarding the initial volume constraints. So in Einstein's theory, you sort of use this conformal trick to write the constraint equations as elliptic PDEs, and then solve the initial volume constraints as sort of elliptic boundary value problem. And so essentially the same kind of methods that work in GR, they also work in these theories to set up initial data, because so elliptic equations seem to be more robust to these deformations than hyperbolic equations. So essentially the same methods that work for GR to construct initial data work here as well.
But again, related to that question could be the propagation of the constraints, right? Like what happens?
Yeah, sure. The constraints propagate. That's fine. There's no issue about that.
Quickly, because we gotta finish.
Okay, so I have a question about these auxiliary metrics. So
Yeah.
How would you choose functions A and B effective?
Yeah. So you can. Sorry, I can't remember the exact bound, but it's very simple. You can, like I said, you can just choose them to be constants, and you can write down very simple conditions that guarantee. I don't know. They have to be like. Yeah, it's very simple to write down conditions that guarantee that they will contains that they will satisfy this nesting property. So it's so in the simulation they just choose constants, so it's fine. But yeah, I mean you could play with different choices, whether whether any of these choices were better for some reason. Yeah.
Well, unfortunately, we ran out of time, but if you have more questions, please come. So let's thank Aron again.
If you enjoyed the video, like and subscribe.